Berkeley, where he is currently doing a postdoc. And he obtained his PhD in 2020 from Yale University, and he has worked extensively on multiple topics related to learning theory, optimization, and so on and so forth. So today he'll be telling us about some hardness results in offline reinforcement learning with linear function approximation. So without further ado, Lin, please take over.
Okay, I would like to thank Chaba, Scherrer, and Berkeley and Nan for organizing this very, very great seminar series. And this has become one of the best top-tier conferences in learning theory and reinforcement learning in particular. Yeah, thank you all. And should I start right now or wait until like 10?
I think you should start right now, I guess.
Okay. Yeah, thank you. Yeah, thank you everyone. Today I'm going to talk about infinite horizon offline reinforcement learning with linear function approximation because of dimensionality and algorithm. This is a joint work with Bruno and Peter, and the work was done was when I was visiting, when I was working for Science Institute last semester. Okay, let's go to some introduction. What's online reinforcement learning? Well, in the usual online reinforcement learning, suppose that's considered a Super Mario game. In the online reinforcement learning setup, Mario interacts with the environment and takes action and observe the state and the reward. And what's the state? And in the Super Mario game, the state is the location of a Mario, and also Mario can be small and it can be also large, and it can like throw fireball or not. So this is also the state of Mario. And at each time, Mario can take 3 different actions. Mario can jump, and Mario can move right, and Mario can throw fireball. And the reward is the number of golden coins that Mario obtained. And how we can play again is formalized by a policy. So what's a policy? Policy is given the state of Mario, how Mario chooses his action. So if we look at this figure, we can see that the Mario, in other words, the agent interacts with the environment, and the agent takes actions and observes the state and reward from the environment. So this is the online reinforcement learning. But in offline reinforcement learning, the setup is a little bit different. In offline reinforcement learning, Mario has no access to the environment, so Mario cannot be in that very interesting environment and interact with the environment. So he has no access to it, but he can learn by watching recordings, which is called the offline data. So if we see here, Mario is here. He's no longer in that environment, but he has a TV, and on the TV he can watch a lot of recordings, and in the recording he can observe the following information. He can see the state of the agent in the recording, and what action this agent takes, and what's the corresponding reward, and what's the next state of the agent in the recording. And in this paper, we study this off-policy evaluation problem. The problem is given offline data, what's the total reward if one starts from a given state and uses a given policy. So this is the off-policy evaluation problem. that we will study in this paper. Okay. Problem formulation. Oh, any questions about if you have any questions about my previous slide or anything, just pause me and ask questions. Okay, let's move on to the problem formulation. In this paper, we focus on infinite horizon reinforcement learning, and we formulate infinite horizon reinforcement learning as an interaction to the following infinite horizon multiple decision process, and it is defined by 5 tuple, S, A, P, R, and gamma, and S is the set of states. And in the Super Mario game, it is all possible states Mario can have. And A is the actions, is the set of actions that an agent can choose and play. And in the Super Mario game, it is jump, it is move right, and throw fireball. And P is a probability distribution, and it characterizes the probability of transitioning to a new state S bar, given a state S and action A. And R is another distribution. It's the distribution of reward given state S, and if the agent plays action A. And we assume that the rewards takes values from -1 to 1, so it is bounded, but one can assume that the reward is bounded by -m to m. We can always normalize it. So we, without loss of generality, we can assume that it is from -1 to 1. And gamma is the discount factor. We will see this discount factor in my next slides. Okay, and policy and value function. What's a policy? Recall that in Super Mario game, policy is a systematic way of choosing the action given the current state of the Mario. So we can formalize policy as a probability distribution of playing an action A given state S. And given a policy pi and initial state as 0, and in the Super Mario game, the initial state is Mario is in the beginning of the game, and he will move right. So that's the initial state of Super Mario game. And given policy pi and the initial state, we will have a random trajectory, and it is given by Si, A, and Ri for I greater than or equal to 0. And AI is sampled from the policy distribution given the current state Si, and Ri is the random reward sampled from the reward distribution given Si and the action that the agent takes. And Si plus 1 is the random next state given the current state Si and the agent's action AI. And in infinite horizon RL, the value of a state is given by the following. It is the sum of all rewards from each time steps, and we have a discount factor here. So in the I step, the reward is discounted by a factor gamma to the I. Okay, and the value of a state action pair, we call the Q function, is given by also the discounted sum of all rewards, but given the initial state S and the initial action A. And since we assume that rewards are bounded by 1, so we have the value of state is upper bounded by 1 over 1 minus gamma, and the Q value of state action pair is upper bounded by 1 over 1 minus gamma also. Okay, and what's reinforcement learning? Oh, reinforcement learning with linear function approximation. This is also a very popular topic in the past couple of years. So it is the following assumption. For every state action pair, S and A, and policy pi, we assume that there's a feature vector phi of SA in RD, and a parameter that depends on the policy pi. We call it theta pi, such that the Q value of the state action pair SA can be expressed as the inner product of the phi SA vector and the unknown parameter vector theta pi. So this is the assumption for linear function approximation. And since the Q value of X and A is upper bounded by 1 over 1 minus gamma without loss of generality, we can assume that the norm of the feature vector is upper bounded by 1 for all state action pairs. And actually, if the maximum of the norm of the feature vectors is greater than 1, then we can use the normalized feature vectors in this. Okay, so we can always assume assumption 2. So in linear function approximation,
Yeah.
Okay.
I was just like wondering whether like what you mean here by without loss of generality, because this will rescale the parameter vector maybe, and also pre-processing the features this way would involve going through all the state action pairs, which probably you don't want to do in a functional approximation context. But maybe, yeah, this is maybe just a side remark, and I think that there is a way of assuming this without even like assuming some pre-processing.
Yeah. I could hear the echo. Okay, so and involves the pre-processing step for the feature vector. Yeah, but if we can do the pre-processing, then we can normalize the feature vector so that the norm is upper bounded by 1. Yeah, thank you for your comment. Yeah. Okay, and in offline reinforcement learning, that's rather than interacts with the MDP Markov decision process directly, the agent has access to a batch of samples, which is SI, the state, and AI, the action that the agent takes, and RI, the corresponding the realization of the random reward, and the SI bar, which is the next state. And we assume that SI and AI are IID samples from a data distribution mu. And so we can imagine mu can be like a uniform distribution over a lot of SI AI pairs, so or even more complicated distributions. And RI is sampled from the reward distribution, and SI bar is sampled from the transition distribution. And formally, the offline policy evaluation problem is the following. Given a policy pi, we would like to evaluate the value of the of a state S approximately, and using samples from U. So this is the OP problem that this paper focuses on. Okay, and another notion is the feature coverage, and we will focus on problems with good feature coverage, and feature coverage is quantified by the feature coverage of the feature covariance matrix. It is the expectation of phi transpose, and S and A pairs are sampled from the distribution mu, and we require that this lambda matrix is well conditioned. In other words, the smallest eigenvalue of lambda is lower bounded. I see a question somewhere. Let me as the samples from one policy or from mixture of policies? Oh, yeah, thank you for the great question. This is from one policy.
Is this really from a policy? It's not from a policy. It's from this mu distribution, and then the mu is over state action pairs, so it's kind of like jumping around. And like, if you sample from a single policy, maybe it will be really hard to get a policy that follows the distribution of mu or something like that.
Yeah, you're right. So S and A are from the. I thought of something else. Also, S and A are sampled from mu, and then given Si and Ai, then we can get random samples. We can get a realization of I and Si bar. So Si, as Chava says, Si and Ai is from mu. It's not from a policy. Sorry. And then given Si and Ai, we can sample Ri and Si bar. Yeah. And a fact is that the smallest eigenvalue of lambda is upper bounded by 1 over d. And this is the best condition we can expect for the feature covariance matrix. There is a very simple proof. We can see that the trace of lambda is given by this. It's expectation of trace because trace is so linear. And then trace of phi transpose is equal to trace of phi transpose phi transpose phi, and this is actually the norm of phi squared. So it is upper bounded by 1. And on the other hand, trace of lambda is upper bounded by d times the lambda mean of lambda, because lambda is D by D matrix. So from this and this, we can get lambda mean of the feature covariance matrix is upper bounded by 1 over D. So this is the best condition we can expect for feature covariance matrix. Yeah. So let's move on to our main results. The first result. So our main results are one lower bound and one upper bound. And let's talk about the lower bound first. We use ID to denote all infinite horizon MDPs that satisfy our assumptions 1 and 2, which are linear function approximation assumptions, and whose feature vectors have dimension D, and the rewards lie in -1 to 1. So in other words, ID denotes all problem instances that satisfy our aforementioned assumptions. And M lambda denotes the set of all probability measures on state action pairs, and such that the feature covariance matrix is lower bounded by lambda. So in other words, M lambda is all data distributions such that it has good feature coverage. And here is our lower bound. If we fix B greater than 1 and Q to be a constant between gamma square and 1, and for any dimension D, which is a multiple of B over ceiling of B over gamma square. In other words, this integer D sub B gamma, which is equal to D over the ceiling of B over gamma square, is a policy integer. And if delta is between 0 and 1/4, then with probability at this delta, we have the rate of the off policy evaluation problem is lower bounded by this. So we take the increment over all policy and all function v hat, and v hat is a function with n samples as input. So given n samples, v hat will ideally give us an approximation to the value of state S. So we take increment over all these kind of functions. And then we take the supremum over all problem instances and all data distributions. Then this sup int is lower bounded by this. And we can see that it is exponential in D, and as gamma goes to, if SQ goes to gamma squared, then the lower bound goes to infinity. And gamma, SQ goes to gamma squared, then the lower bound goes to infinity. And the Q here is the characterize the condition number of the Fisher covariant matrix. Let's see here. Because in the supremum, it is taken over MQ over D. That MQ over D is all the data distribution with lambda mean of lambda greater than Q over D. So if we allow the data distribution with the condition of the covariant matrix lower bounded by gamma squared over D, then the lower bound for the sample then the lower bound will go to infinity.
Hey Lin, can I have a quick question? So can you say again what's maybe the intuitive interpretation of this B quantity? What does it correspond to, and how it? One thing is that I don't see how it is manifested on the left-hand side of the bound, but it appears on the right-hand side. Can you say a little bit more about that?
Okay, so B is just any fixed constant greater than 1, and actually the assumption of this theorem requires B gamma squared greater than 1. So we show a lower bound when this is satisfied. And maybe it would be more helpful if I can go to the next slide. I explained a little bit here. So this lower bound, this result identify a hot regime D gamma squared greater than 1. If D gamma squared is greater than 1, then there is this B greater than 1 such that B is greater than or equal to B over gamma squared. Then we can take B to be the ceiling of B over gamma squared. So I introduced B here basically because there are some rounding issues in constructing a hot instance that I will explain later. So basically, if there's no rounding issue, we only need D gamma squared greater than 1, actually. So this is the hot regime that this result identified. Does that answer your question then?
Yeah, then was the question answered? I have other questions.
Okay.
Munch. So someone on YouTube was asking, we have YouTube watchers who are asking questions. That's great. Whether this data was like with probability 1 minus that, or with probability that. On the previous slide, it was with probability data, and then here I see with probability at least 1 minus that, and like
yes.
Which one?
It is delta. It is delta with some positive probability. This lower bound result holds.
Okay, and in the log, I see a data and a 1 minus 2 data as well, so that kind of like made it symmetric. But on the next slide, can you go to the next slide? I see a probability at least 1 minus data. So is that a data too?
So for the sample complexity to hold, it happens with probability 1 minus delta. So it is correct here.
Oh, like data is an error probability. And if we are on the error event, then the lower bound is high, or something. Like, can we go to the previous slide?
Yeah.
And if you are on a good event, what? I'm confused about this data and 1 minus that. I would expect to see 1 minus that on both places, especially since this says with probability at least data. I have a related question to this. Maybe this is going to clear up my confusion. And also, Shipra had a question about the v hat. So what is random here on the left-hand side? And like, how is the, like, what is the source of the randomness, given the fact that we are taking a supreme over all these things like the MDP? So usually it's like the MDP and the sampling distribution induces a joint distribution over the sample, and then that's the source of the randomness. But here the supreme is over all possible MDPs in this set ID, and the mu is also like, it's a little bit confusing for me that we have this soup and inf, and then there's the v hat. Like, what is like the source of randomness here? How do we make sense of this? I guess if I wanted to say this verse, then maybe it would be like with probability at least 1 minus data, there exists an MDP. No, like I would say there exists an MDP. No matter what your algorithm is, I can choose an MDP and I can choose a mu in such a way that your algorithm goes and then like works on the samples, produces v hat, and the gap between v hat and v pi is going to be at least this large. And this is what happens with probability data, or some at least probability data, or probability at least 1 minus that, right? Is this the statement? I guess.
Yeah, and so first of all, I would like to explain the source of randomness. The source of randomness is from our sample from the data distribution.
Yeah.
And in the Hop instance, there is no randomness except for randomness from the data distribution.
Right.
And what's your second question?
Well, I guess I guess this was all together. Like, Shipra was asking, okay, what is v hat? What is the restriction on v hat? Because like it's not clear from the slide why can I choose v hat to be v pi of s. But I guess like no, v hat is the value produced by this algorithm whose input is the sample and the distribution.
No, but Chava, so Shipra and I just had some discussions. So
Okay.
even if it's a function of the samples, because it's inside the supremum, in principle, it could get this additional oracle knowledge about
Like
what
the
v pi is, right?
Like
So it seems like at the minimum, the inf over v pi, v hat should be put outside of the supremum, right? You need to fix the estimator first, and then let the adversary choose the worst case MDP. Right. Otherwise, as Shipra said, like there's a degenerate issue here.
This is related to my question because this inf soup is very super confused. It's like, okay, it's first for its soup inf, it should be inf soup, and also like I don't know whether you can. I think like I don't know whether you can write it this way.
Actually, soup inf is actually stronger than inf soup. Because in this Hop instance, I'll present a Hop instance with all deterministic, with only one action for each state. So there's only one policy. So everything's deterministic, and there's only one action for each state.
Yeah, no, but Lin, I think Shipra's point is not about the inf over pi part. So you're talking about the inf over pi part. We're talking about the inf over v hat part.
Yeah.
Like your current formulation allows the v hat to just take the value of v pi straightforwardly. So the lower bound is 0.
Yeah, I think the problem is like when you do inf, you have already fixed pi.
So you have already fixed the MDP, right?
Yeah, and you fix pi. Oh, yeah, you have already fixed the MDP, and you're doing inf over pi and v hat. So I can just choose pi anything, and I can choose v hat to be v
equals v
pi. So
pi,
inf will
right?
always be 0.
Ah, I see. Let me think about that. Yeah, maybe I should put. Yeah, maybe I should put v hat somewhere else. I don't know. I'm not quite sure right now. Yeah, but we are great point. But maybe
I think the algorithm needs to be fixed first. I don't know what the rest of it is, but it seems like the algorithm needs to be fixed first. So it needs to be outside the soup. But I don't know, like what your result statement, how you want to restrict v hat in some sense.
yeah, I think it will become more clear when I present my hot instance later. Yep. Yeah, thank you for the great point. Let's see our hot instance later. And let me just interpret my lower bound a little bit. So if we translate this rate, the lower bound for the rate, we can get a lower bound for the sample complexity. And this sample complexity lower bound is exponential in D. And if Q is gamma squared, then the lower bound becomes infinite. And there's two related work I would like to mention here. One is the related work by Amaltila. I'm not sure if I misspell his or her name at all. And they get a result that when the covariant matrix, when a feature covariant matrix has lambda mean equals gamma squared over D, then even infinite data is not sufficient to approximate the value of a state. So actually, this result includes this previous work as a special case. This is one result I would like to mention. And there is another related work here by Andrea Zenti. It is a single, this paper is a single author paper, and he also derived a lower bound for infinite horizon of policy evaluation problem. But I compare the lower bound in this paper and the lower bound in his paper, and I see that his result. So sometimes my lower bound is better, and sometimes his lower bound is better. So I would like to mention here a very recent work by Andrea here. And let me describe the second main result, and then I will go to the construction of my hot instance. So to prove an upper bound, we need an additional assumption. This is the low distribution shift assumption. Before that, let me introduce some definitions. Recall that the feature covariant matrix is defined by the expectation of phi transpose, and we define tilde phi to be the expectation of phi SA, the feature vector, and the expectation is taken over A given the policy pi, and we would like to approximate the value of x0, and we define lambda 0 bar to be phi tilde transpose of x0. And we define lambda bar to be the expectation of tilde phi s bar and tilde phi s bar transpose. And the low distribution shift, which is a assumption also assumed in Wang et al. This paper studied the of policy evaluation problem for finite horizon MDP, and they and they assume a similar low distribution shift assumption. And here in infinite horizon of policy evaluation problem, we assume this additional assumption. This assumption says there exists a C which is between 0 and 1 over gamma squared, and there is a C0 greater than 0, such that lambda bar is less than C times lambda, and lambda bar 0 is upper bounded by C0 lambda. And this means that C lambda minus lambda bar is a positive semi-definite matrix. And here it means that C0 lambda minus lambda 0 bar is a positive semi-definite matrix. Okay. And again, we use ID to denote all infinite horizon MDTs that satisfy our assumptions 1 and 2, and the future vectors have dimension D, and the reverse lie in -1 to 1. And we use M bar to denote all probability measures on S times A, such that this additional assumption 3 holds with constant C and C0. Okay, and the lower bound result is this. Assume that C is between 0 and 1 over gamma squared, and C0 is greater than 0, and let eta between 0 and 1, such that C is less than 1 over gamma squared minus alpha, and beta is some constant less than 1. Then with probability at least 1 minus delta, we have this minimax result. We take the increment over V hat and supremum over all problem instances, policies, and data distributions, and the state we would like to evaluate. And it is upper bounded by this, where n is the number of samples from the data distribution mu, and V hat is a function with n samples as input. And this rate is achievable by algorithm, this D square policy evaluation algorithm. We will talk about this later. If we set this parameter in this algorithm, then with probability 1 minus delta, we will have this rate. Here we ignore all other constants. So the rate is basically it's basically over n to the 1/4, because we have a square here. And
yeah, is am I remember? I thought this problem, like 1 over root n rate, should be possible. Can you comment on that?
1 over root n rate, right?
Right, root n instead of the quarter.
What's the assumption of this rate? So is there any like assumptions?
Yeah, I'm trying to think, but yeah, I just wonder, like, if you think the 1 over n to the quarter rate is the best upper bound, or is root n plausible? Because the algorithm in my mind, I would try maybe something like LSTD, but you will need to assume an additional matrix invariability assumption. But if that assumption passes, I would think that 1 over root n would be straightforward. Yeah.
Okay, I'll check with you later about. So it would be great if I can have some reference to the result that you just mentioned, if it is already online.
Oh, there is a paper by Magdi as well a while ago. That was a 1 over root n result. But
No, but Chaba, that would require low inherent Bellman error.
yeah.
So here they only have realizability, right?
But I see that, like, you're saying that, oh, like with some additional assumptions, we could have some better result.
Yeah, but I mean, low inherent Bellman error, I feel like that's too much additional. Whereas LSTD, like representation-wise, roughly speaking, only requires realizability. So maybe that's more comparable.
Okay.
I see. Thank you. Yeah, thank you for this great comment. Yeah, I think personally, I think this result can be improved. So I'm actually working on this. I'm not fully satisfied with this yet. Yeah, but great point.
I have a question about this, like the way the result was formulated on the previous slide. It seems that there is a uniform convergence type of thing going on, because the result says with probability 1 minus data for any MDP in this class, and for any mu, and for any S naught, and policy pi. So like you have an error even that holds for all of this, and I wonder whether that can really be proven. That seems like pretty strong. I would expect that, like, for any fixed MDP with probability at least 1 minus delta, this error bound holds. But what is written here is that with probability 1 minus delta, for any MDP whatsoever, this error bound holds. The ordering of, like, where is the MDP? Like, is it outside of the error event? Is it inside the error event? So is it like you have a uniform convergence type of result? The error event, how is the error event even defined? Whose probability we're talking about here? This probability data event, what is that?
Right, because I guess like what could happen here is that, well, you just, for every MDP, right, you realize the data sets, right? And then you just give the worst possible data set to your algorithm, and that is going to be terrible.
Yeah.
Right? I don't think that you could deal with that so simply.
Yeah.
So the upper bound here says that for any MDP instance, and if we sample data from that distribution, then this algorithm will with probability at least one minus delta will give us this this guarantee.
So it is just like that. This is like the way it's written on this slide doesn't suggest this, but like this makes sense. Okay, good. Thanks.
Yeah, thank you. And then least square policy evaluation is just a very classical algorithm. So let's have a quick review on it. We take samples from the data distribution and we form the data covariance matrix, but plus lambda times the identity term. And in each iteration, we compute the estimation for theta hat, which is lambda hat inverse times this quantity. And then we have estimation for Q hat of SA, and we have estimation for V hat. And this upper bound, the techniques of this upper bound is very similar to the one et al. Paper that I just mentioned. But there are also many improvements and different techniques I introduced in this upper bound. But due to time limit, I will skip the proof for the upper bound and focus on the hard instance construction. And here are some interpretations of the upper bound results. So the assumption of the upper bound is basically lambda mean of lambda is greater than gamma squared. So recall that if lambda mean of lambda is upper bounded by gamma squared, then it is generally impossible to approximate due to our low bound result. And if lambda mean of the covariance matrix is greater than gamma squared, then the assumption 3 holds with some constant C and C0. So here is the argument. If this happens, then we know that there is some constant c such that 1 over gamma square is greater than c and greater than 1 over lambda mean of lambda. Then we have these two inequality holds. So assumption 3 holds. And from this upper bound results, we know that if we have this many samples, which is basically 1 over epsilon to the 4. But as Nan suggests, this can, I also agree that this may be improved. And after log 1 over epsilon rounds, we have the additive error is upper bounded by epsilon. And if we assume additionally that the norm of the parameter is upper bounded by root d, as assumed in these two papers, then we need d squared over epsilon to the 4 log d over delta samples to guarantee that the approximation error is upper bounded by epsilon. So these are the three interpretations of the upper bound. Okay, so let's move on to the proof idea for the lower bound. So here, this is the hard instance, and the technique used here is the error amplification technique introduced in Wang et al. And also the construction of the construction in Amartya paper that says infinite data cannot suffice. So let me have a overview of the hard instance. So we have m times L times 2 plus L states here. And they are divided into 3 groups. And n is an integer. We will determine later. And in group A, we have m times L states. And in group B, we also have m times L states. And in group C, we have L states. And we divide the state into L levels. So this is level 0. This is level 1. This is level L minus 1. And the same similarly for group A. This is level 0, level 1, level L minus 1. We can see that there is a double subscript here. So each state in group 1, group A and group B is indexed by 2 indices. The first one is the level, and the second one is the index in the level. In this level, and m is some integer greater than 1 over gamma square, and we actually can take it to be the ceiling of b over gamma square. And let R0 be a constant which can be 0 or 2 epsilon over gamma to the L minus 1 ml over 2. And for these three groups, and we define the reward to be this. So for group A, the reward is all 0. So in group A, the reward is all 0. And all states in group A will deterministically go to the corresponding state in group B. And for group B, it will go to the state in group C, but of a lower level. So everything is deterministic, and there is only one action for each state. And for group C, it will go to the state in group C, but of a lower level. Okay, and the reward in group A is 0, and for states in group B, they have reward 0 if the level is greater than or equal to 1. So in group B, from here to here, they all have reward 0. but on lower 0, it has a non-zero reward. And it is actually this, with probability 1 plus R0, 1 minus gamma over 2, the reward is 1. And with some with this probability, the reward is -1. And in group C, we give if the level is 0, i.e., I mean in this state, the reward is this. And on level 0, on level L greater than 0, the reward is this. And we can compute the value of each state. So the value of a state in group B is this. If this state is on level L, and we can see that the value of state in group A is just gamma times the value of the group, the value of the state in group B. So we have additional factor gamma here. Okay, and we can also compute the value of group C states. Okay, and we can, and the state we would like to estimate is this state. And the data distribution will be a mixture of uniform distribution. So the data distribution will be a mixture of uniform distribution on group A and the uniform distribution on group B. So we'll go back to this later, but so we will not have access to states in group C. And this is the and then ELI to be the standard basis of the d-dimensional Euclidean space, and D is M times L. The feature vector for group B is just E sub Li, and the feature vector for group A is just gamma E sub Li, and group C is this, and this is our parameter for the policy. And the high level idea is this: if we want to find the value of this state, which has only two possibilities depending on the value of R0. If R0 is 0, then the value of this state is just 0. And if the value, if R0 is this, is 2 epsilon over gamma to the L minus 1, M to the L over 2, then the value of this state is 2 epsilon. So if we want to determine the value of this state up to L epsilon, then we need to determine if R0 is either 0 or this non-zero constant. Okay, and if we go to next slide. So here we describe the data distribution. Again, the data distribution is a mixture of uniform distribution on group A and group B. And recall that this is the feature covariance matrix. If the data distribution is uniform of group B, then we can see that the feature covariance matrix is just identity. And if the data distribution is the uniform distribution on group A, then the the feature covariance matrix is just gamma square identity. And because we let mu to be a mixture of uniform distribution on group A and group B, then the feature covariance matrix will be somewhere in between. So we can make lambda min of lambda between gamma square over D and 1 over D. So this is the mechanism. And then the high level idea of a strategy is this: we would like to reduce it to a learning problem. So to be precise, if we want to approximate the value of this state, which is the highest state in group C.
Hey, Lin, just a reminder, we have maybe 2 minutes left in the official time. So yeah, maybe you need to plan your time a little bit, I guess.
Yeah, thank you so much. So if R0 is 0, then the value is 0. And if R0 is this, then the value is 2 epsilon. So to approximate it up to epsilon, to approximate it up to error epsilon, we have to distinguish these two possibilities. So the problem is this: we have two distributions. One is when R0 is 0, and one is when R0 is this thing. And we get samples from this distribution, and we would like to distinguish which distribution we have, either just uniform, just a plus or minus one uniformly random, or we have some bias distribution on minus on 1 and 1. So then we reduce it to a learning problem, and using some classical result in learning theory, we know that we know that how many samples we need to distinguish these two distributions, and we need this many. If we have n0 samples, then with probability at least this, any algorithm can output a incorrect value from the two choices, 0 or 2 epsilon, and we can translate it to a lower bound on the sample complexity, which is this. So given n samples, then we get the lower bound for the error, which is basically exponential in D and root 1 over n. Okay, just to recap, in this paper we identify a hard regime d gamma square greater than 1, and for any q between gamma square and 1, there is this hard instance such that the smallest eigenvalue of the data of the feature covariance matrix is greater than q over d, and the off-policy evaluation requires exponentially many samples. And when q equals gamma square, even infinite data cannot suffice. And for the upper bound results, if we assume additional low distribution shape assumption, we show that this many samples will be sufficient to guarantee approximation with error bound epsilon and probability at least 1 minus delta. Yeah, thank you so much.
Hey, thank you.
Thank you.
Yeah, let me see if there are any questions. Yeah, so please ask questions. If I didn't make something clear.
So I guess you don't need to read whatever we were writing in the chat. We can just say that, like with Nan, we had a little discussion about how come LSP works in this case, and the conjecture kind of is that you're very close to the on-policy case, and in on-policy case, the Bannerman operator would be a contraction, this L2 operator, L2 norm contraction. So it's a classic result. And then that would imply that you can find a fixed point by iterating it. And then that kind of like puts everything in place. And so somehow the assumptions are ensuring that we're close to this case. So I wonder whether this is really the gist of the proof, or what do you do in a proof?
Is it the reference that you mentioned in the chat?
Yeah, there are a bunch of references, but maybe to turn this into a question, like for the proof of the upper bound, like how does it work, like the very, very high level?
Oh, okay. So for the upper bound, let me go to the slides here. So this is basically, I think that the central idea is that the matrix concentration bound. So if we have many samples, then we can approximate the matrix pretty well, and then we can do pretty precise estimation. So I think that's the central idea.
No, I think we're more interested in. So I mean, like all these proofs have two parts, right? It's like one-step concentration on data is one thing, but another thing is how error propagates from step to step, right? So the error accumulation and propagation. So I think we're more interested in the case where in the question of how do you control error propagation? Because, for example, in the work of Duan and Mondi Wang, like they assume the Bellman closeness, which helps you control error propagation. But here you only have realizability, right? So you don't have closeness. So I think that's the question of how do you control error propagation?
Oh, okay. So actually, I would like to mention one very major difference between our paper and the paper of Wang et al. The difference is that we have a constant beta here. So in the infinite horizon case, we can control the bound by making some term shrink by every step. So there is a term here. So that's why it's very important to make beta less than 1. So if we can make beta less than 1, then some term will go to 0 as t goes to infinity. And it's relatively challenging to describe the technique in 1 or 2 sentences, but I think there are many differences between finite horizon and infinite horizon, and a very important point here is to construct the infinite series with constant shrinkage at each step. Does that answer your question? Or maybe I could provide more intuition about that.
Yeah, I think I get the gist of it. Maybe Chaba has more questions, or we should also open the floor to other questions.
Yeah, I just do that.
So maybe I can ask a quick question. So just to get the understanding of where this result falls, do you assume that you know these bounds on like how the eigenvalues, the range of the initially that you mentioned, the range of eigenvalues, like compared for mu versus the policy that you are looking at?
Are you referring to the upper or lower bound result?
All right, the upper bound doesn't have any of those range. So in your upper bound, you need to know mu, like the algorithm needs to know mu.
In upper bound result, we don't have access to
Oh, you have samples from mu.
Yeah, we have samples from mu, but we don't have access to mu directly.
Right. Okay, yeah, then it's fine. Yeah. Sorry, yeah, I got confused between the policy assumption and the distribution assumption.
Yeah, but I have a question also about this, which is that, well, for LSP, there's this hyperparameter is like the number of iterations? Like, how do you set that? Because it seems that, so that is capital T here, right?
Oh yeah.
But if I'm just looking at this upper bound, it says that, okay, set T as 0, and then this is the best choice. So what is the condition on T that I'm missing here?
No, there's a beta to the 2T term.
Yeah.
No, so you want T to be large, no?
Oh yeah, sure, yeah, right. So
Actually,
yeah, right, that's correct. Yeah, sorry, no.
Yeah, if we want to guarantee that the error is upper bounded by epsilon, we actually need T is greater than log 1 over epsilon, and this many rounds will be sufficient.
Yeah, right. Yeah, no, sorry, I missed the scale of beta. Okay, but then regarding this beta a little bit more. So like, what exactly is your assumption regarding that? Because the way that was phrased was like a little bit too complicated for me. It had like another parameter eta in there. And does this eta appear in the bounds as well?
Eta actually characterizes how close the condition. I mean, if the condition is very bad, if it's close to 1 over gamma squared, then that would be hard. So eta is basically the gap between them. So how bad or how good the condition is.
Yeah, so what is this condition? I think this is what I was missing in my question. Like,
oh yeah.
Can you explain again what this condition is?
Yeah, great question. So the condition here is it's in assumption 3. So so we require that C is between 0 and 1 over gamma squared. So C cannot be gamma squared, and C cannot be 0. And we need these two inequality to hold. So and eta is basically how close C is to. So I mean, how close is it between C and 1 over gamma squared? So eta characterizes the gap between C and 1 over gamma squared. That is the condition that I just mentioned.
Yeah. So Scherrer, if you look at the definitions here, so gamma is the data covariance matrix, so lambda or lambda, I guess. So lambda bar is what happens when you evolve the data for one step and you take the action according to the policy you're evaluated, and take the covariance matrix on that distribution, right? So really, this is saying something like nearly on policy, because if you're fully on policy, then S bar and A bar would have exactly the same marginal as S and A, right? So in that case, C and C0 would be something like 1, I guess.
But you don't have a way to know C0, right? Like,
I guess you don't, but your algorithm, at least LSPE, probably doesn't need to know that.
Oh yeah, you need to know beta, right? I mean, you need to know beta in order to know. Sorry, I hear an echo. Okay, so you need to know eta, right? Which is like the gap between C and 1 over gamma squared, if you want to know what beta is, and you need to know beta if you want to set T, such that beta to the 2T term becomes like indeed small enough. So you do need to know this parameter.
But that only appears in your bound, right? I mean, the algorithm, you just do LSPE for infinite number of iterations.
Well, the number of iterations, right?
Yeah,
no. Infinite number of iterations.
Yeah, you just run infinite, and if it diverges, right? This is saying that if everything is satisfied, you just won't diverge. So if it diverges, you just explode and give up.
So is divergence the only catastrophe that can happen? Can we converge to the wrong thing?
It could, but I mean, I guess my point is that if those things, under those conditions, there's, at least according to the current results, there's nothing else you can do. Or maybe here's the saying, there's no situation where knowing the beta gives you more algorithmic advantages, at least according to these slides. That's my understanding.
Clarifying question related to this. So in this algorithm, we have two parameters, capital T, we discussed that, and lambda, right?
Yeah.
So for the first result, On the right-hand side, I don't see lambda at all. Like maybe it's there, but I'm just missing it. So lambda was this regularization parameter, line 3. On the previous slide, in the upper bound, the first display, it doesn't depend on lambda.
There is a lambda setup, I think it in terms of C1.
Yeah, there's a 1 on the bottom. Oh, okay, you need to know C1
no,
for
like
that one.
first,
Okay.
but like, talking about the first is that, yeah, I know that later on, like the lambda is going to be chosen based on that, but like I really wanted to know, like, is the first result, does it hold for any lambda, or what's going on? Like I'm missing something there, I'm sure.
Are you asking if the first result holds for any lambda?
Yeah.
Oh, actually, so if in this result, actually there's no lambda involved. So this race is achieved by LSBE with this lambda. But when I state this first result, there's no lambda in
because there's an inf over v hat. So essentially, LSPE for any specific lambda, I guess, is just a special case of the v hat. So you have the freedom to choose any lambda you want.
Yeah, this is a there exists an algorithm type.
Oh wait, but wait, no,
right.
But your lambda need to be set in a way that is
right
according to the mu distribution and the MDP and stuff like that, right?
Yeah, like.
So that's not, it's not entirely clear. At least the way you write it, inf v hat this time is completely outside. So it must be hyperparameter free.
Yeah, like the eta is not known, right?
Yeah, great point. Yes, the choice of lambda depends on the optimal lambda here depends on eta, and eta is the gap between c and 1 over gamma squared.
Yeah.
Yeah, I think the first result is that there exists some V hat such that all MDP satisfy. The second result is for any given MDP with these conditions, you can set V hat to be this way, and then you will get.
No, I have doubts about the first result.
Yeah, I think it's just the usual mess stuff with all the like crazy minimax way of writing things, right? Because Lin says particularly, I assume that basically the first result is actually essentially proved by or a corollary of the second result. That's what I imagine.
Actually, yeah, you're right. So we get this first inequality actually from the second inequality.
So just to not to go, final questions on this eta stuff. So how is eta related at all to? So it seems lambda depends on eta and eta depends on c. And c is, does c depend on mu versus pi or not? I think it does, right? So you do need to know eta in order to run your algorithm.
Yes, I agree. Yeah.
You can run it, but like you won't get the result, right?
Yeah, but if we know that the instance holds, I mean the assumption 3 holds for your specific instance with constant c and c0, then you can run your algorithm. So if you know that your instance satisfies assumption 3 with parameter c0, then you can choose lambda.
Right.
So can you then just do like something like cross-validation or like a grid search over lambda. You just run LSP for a very long time for all choice of lambda, and then whenever it converges, you say that, okay, this looks like the right solution. Do you think that this would be possible? Or is there a caveat to this?
I mean, I don't know how you will check. That's again another policy evaluation problem. Like, how will you know?
Yeah, thank you for the question.
And maybe I had some more questions regarding the lower bounds.
Okay.
Like the actual statement that had all these like Q and B parameters in them. So I was just still parsing that. So essentially this is saying that, well, you're going to have something that is exponential in the dimension where the base is, like the base of that exponential is going to be B. So essentially your assumption is that, well, this B is a constant, right? Such that this really represents exponential growth.
Yeah, B is a constant. And then D sub B gamma is proportional to D. If we view B and the gamma square as constants.
Okay, so if I look at this exponent, then that becomes like B to the D over B. So how does this behave for? Okay, well, I guess B is some constant. It's fixed. Okay, that's good. No, so we don't care about how this grows with B. Yeah, sure.
I mean, does it? Can I set something weird like B equals root D or something if I want to maximize growth or something? I don't even know if that optimizes the growth, but something.
I think the optimal B is equal to E. If B is equal to E, I think it is optimal. I mean, the lower bound is maximized.
Maximized? Okay. Right. Okay.
I just want to make it more general, so I allow B to be any constant greater than 1. Because I would like to cover almost all. I would like to cover the situation where D gamma square greater than 1. If D gamma square greater than 1, I would like to I can construct a hard instance. So B is not necessarily E, but if B is equal to E, then the lower bound is maximized.
And that is absolutely correct.
Yeah, so the lower bound also depends on our desired condition number, right? So if we want it to be best conditioned, then the lower bound will be smaller, and if we allow it to be very bad conditioned, then the lower bound will be larger. Yeah, great question. And actually, dB gamma here is just the M in our construction for the hard instance. And here, yeah, as I wrote here, oh, sorry, dB gamma is the number of levels, sorry. And M is the ceiling of D over gamma square.
All right, yeah, so that explains what B should be. Yeah, well, 2 or E. Yeah.
Did I make the lower bound clear? I mean,
yes.
The hard instance clear? Okay, yeah, that would be great.
Right, so does anybody else have questions?
I had one with respect to the next slide,
Okay.
and the theta pi of the norm of that. I had a query with respect to the assumption, which you took from, I think so. There was a paper, the 13 and the 23, which you referred in your. It was from one was from Kakaday's paper, and the other assumption that you referred was from the assumption A in the Zin's paper. I was wondering why it's order of under root D. I was thinking of the assumption might be expanded based on the condition that we have. Could you please clarify that a bit?
So are you asking how the condition influences the lower bound?
No, with respect to the on equation. Let me check the slides. The hard problem that we have on the where was that equation? Yep, the upper bound, the main result to the upper bound.
May I have your question again?
Here I'm referring to the theta pi of the norm here that we have. So I was wondering what was the assumption that you took, and can this be expanded a bit with respect to the additional errors with respect to the q pi minus the qt hat, which is at most epsilon. So because of this, it was assumed that the spectral norm here is upper bounded by the order of root d. So here.
So would you like me to give more justification of this assumption, or?
Yep. Yep.
Okay, so there are a couple of justification for this assumption. There's one justification for the assumption in one Kakade and another author. So one Kakade et al. And there's a footnote in their paper. They said that because the value because of the Q value of SMA is upper bounded by in their setting it is like some constant times h, right? If I recall it correctly. Then they said that there is this coordinate system such that this is true. So there is this coordinate.
Yep. Yep. They have upper bounded by h and root d. So yeah, I was wondering the coordinate and how this transforms to here. So yeah. Thanks. I got the gist.
But actually, I was personally not that convinced by this justification because we do not know this specific coordinate system a priori. So yeah, if anyone can give me a more convincing justification, that would be great, because I was also not that convinced with by this justification. And this assumption is also assumed in Qijing. His paper also assumed this, but as far as I can recall, he didn't write much about the justification of this assumption. Yeah. So Chaba and
yeah, you can actually justify this. It's a pre-processing step. It's like you could say that like I run my G-optimal design, and then I retransform the features based on that, and like it's all fine. Like I was also wondering about this, and then I had a discussion with Ruosong, and he convinced me that it's fine. And then I convinced myself that like it is fine. It is a pre-processing thing. Like if you just start with G-optimal design, then after you have your optimal design, you can use the moment matrix of the optimal design to retransform the features, which are going to ensure that like the corresponding transformation of the parameter vector is such that this is going to hold. It's fine.
Even if you know the features vector and we don't know anything else, so given only the knowledge on the feature vector, we can guarantee that.
It's basically like I reduce everything to Kiefer-Wolfowitz. So Kiefer-Wolfowitz says like whatever feature map you have, if it's full rank, then the worst case blow up errors are controlled by square root D, and like this is a version of that.
I see. Is there any paper that have detailed description of the justification for this assumption?
No, this paper is as detailed as it gets, as far as things are written down. Maybe since I'm writing up lecture notes for my class, I would just add some notes somewhere, and then it will be there with some more details. I would just make a note for myself. I'll let you know. Okay. I did have one question, but I don't know whether any other people have questions. It is a general question about the lower bound and the upper bound. They're quite far apart, right? Like in the upper bound, we are close to the on-policy case. In the lower bound, we are absolutely off-policy. And there is a whole spectrum in between. And I was wondering about, like, have you wondered about, like, how the spectrum should look like? What is in between?
Yeah, great question. To be honest, I haven't thought about that, but yeah, it's a super interesting direction, and yeah, I believe that there is something in between, and maybe we can interpolate these two extremes.
Yeah, one would think so. I don't know how, but I think it's kind of interesting.
And there is definitely many future work to do. For example, the current upper and lower bound have not matched each other yet, and as you suggest, if we consider the spectral, maybe there's a way to connect these upper and lower bounds.